But let's summarize the language. It's basically is generalizing the idea of the Fourier expansion and use and the same language you can apply to other expansion. Doesn't have to be restricted to sine and cosine. Any uh, basis function becomes you can use the same language. So remember so far we have the formula that f of x. This x is you can say defined within minus pi to pi, right? Or 0 to 2 pi, that's at least one period of this function. And actually, when we actually want to expand, it doesn't have to be periodic. It's just the domain is the length, you call it 2 pi, at least in this form. And in a bit later, we can do an arbitrary length. And then the result will be just redefining your x. But in this formula, so last time we defined that, when we already said that S, then if you use the complex one, it's quite trivial. It's INX, right? That's trivial. And then you can also equivalently write it in sine and cosine. In that case, the constant term has a slightly different form. You divide it by 2, and then the other term, this cosine and sine. Okay, and then we divide the formula for C sub n. So C sub n is integrate over the period of x, right? And likewise, you can translate the equivalent formula to calculate a sub n and b sub n, and we divide that. Basically, it's not not multiplied by this exponential function. You multiply by for a sub n, you multiply by cosine, b sub n, you multiply by sine. And normalization for this is instead 1/2 pi is 1/2. So you know all those formulas, the difference. And we did that, but the last time by this more general theory, we put it in the language that we define all these exponential function becomes the basis, and we define the basis that already normalized is defined as, for this case, is 1 plus square root of 2 pi. Right, and then for the cosine and sine series, the phi n is slightly more complicated. You define, and last time seems like there could be a confusion. This phi is a notation of the basis that you're using. It's not saying that if you write phi n, define all the phi here using sine and cosine. I'm not saying that these are the same correspondingly. They are not the same. You're just choosing your basis, like 0 is a 0/2. And yeah, 1/2 pi. And then phi, n positive ends are the cosine. Normalization also slightly different. And phi minus n sine. This n is okay. But using this notation, and we can write this expansion in a uniform way. And first you define the scalar product. So any scalar product is defined by the formula in your textbook. You're using F and G, not exactly this same. Now it's a general form, just arbitrary function F and G. For the Fourier series, the domain is minus pi. The pi is defined as integrating over the domain. So F complex conjugate. So define as minus pi to pi for our domain. And your textbook using 0 to 2 pi, that doesn't matter because all these are periodic. Okay. And so define this scalar product. And for using sine and cosine, obviously the complex conjugate doesn't matter if those are real, but you just keep it just for a general formula. So in that case, first all these bases are normalized. So either you use this set or that set, you can check for yourself, convince yourself that the scalar product between two bases is just the conical which means it's 1 if the two are the same, n and m are the same, if 0 if the n and m are different. Okay, so this is called the orthonormal condition for the bases, right? Both sets are the same. And then you can write the expansion. Now using this this general notation as sum over n, and then just a scalar product between phi sub n and f, and then okay. In both cases, this or that, as long as you're using the respective definition of phi sub n, using either this set or that set, you can put the both either expression as it's a uniform formula. It's okay. So that simplifies things. I mean, you don't have to remember that this is the formula for exponential function, a formula for cosine and sine, and then you can generalize it. If you're not using sine and cosine, using other function, transfer function, or whatever that you will learn later, it's still the same. As long as you change your choice of basis, the expansion is just like that's the same. The scalar product can sometimes change a little bit, but this form is still the same. Okay, and last time we also said that all this assumption that you can do an expansion of a function using these bases is called completeness. And after you prove the completeness, which is a separate subject, which may be more difficult for us to discuss that. But so the fact that you can do that is called completeness, and the consequence of the completeness is that you can divide the completeness condition, and last time I think we divide that as basically sum over all the bases, and then this phi sub n phi sub n of x prime. I think that's a complex conjugate, and phi sub n as we define the Dirac delta function. Right? And that how you see that is basically substitute that say substitute this C sub n or this definition. I mean, that's the formula for C sub n back to here. Then you have integration, right? And sum over that. You put the integration out, the sum over all this two multiply together, right? And then you integrate over the range is then give you back exactly the same. When you put it to in this formula, you change x to x prime because you already have an x here and then x here. When you substitute this in here, this changes to x prime. But in order that the integration give you back the fx, whatever inside the integral other than f would have to be a delta function because that's just the property of the delta function. The delta integrating a delta function multiplied by any function integrate over the range is give you back to the function at the value when the argument of the delta function is zero. Okay, provided this the zero is within the domain, within the integration range. Okay, so that's how you get the completeness condition. Okay, and so that's a little easier to see for phi sub n. They substitute this into this. This becomes just sum over this. For this particular case, it's just sum over n. And you have 1 over 2 pi here. It's exponential function, all right? And one is compact conjugate. And this is a relationship. The property of completeness. Say this is the consequence of completeness. Right? And likewise, you can use this and do this. Put this all these psi for cosine and sine, put it in here, and convince yourself that this also works. For completeness, you can also write down the expression for sine and cosine. But as it turns out, the sine and cosine term they respectively has a completeness condition. When we discuss the Fourier cosine series or Fourier sine series, they actually form a complete set of self, or the sine term or the cosine term. But anyway, we'll go to that a little later. Okay, so that's all this theory, and one kind of a side note. Sometimes people, especially doing quantum mechanics, so would say that this is like instead of calling this a function, it's like this is like a vector in a vector space, and then this if you think of this as a vector, all these are vector bases, like a unit vector in a three-dimensional basis, all these phi sub n, and to indicate that they are like vectors, sometimes you're writing is like f. This is what we call the bracket. This is a cat vector. This is a cat vector, and then put it in. Some of you learned quantum mechanics before, so right? Yeah. So that all these phi sub n is also using a cat. This basis you also use a cat vector to represent that. Okay. Some of you that haven't taken quantum mechanics is maybe this is just a preview, or we'll talk about that a little more later. That is the indication. So this equation becomes like just like you decompose vector, like a vector in three-dimensional space. You decompose it in x, y, z unit vector or whatever unit vector set you use spherical coordinate or cylindrical coordinate. It's like you project your vector into the unit vector, and the component on that unit vector along the unit vector is the dot product or the scalar product between the vector and the basis. So you vector dot into the basis unit vector multiplied by the unit vector, sum over all the unit vector is your vector itself. So you represent a vector in unit vectors basis, and you can in this kind of notation, you can easily see you can change your coordinate system. This is in this case like change a basis function. That's possible. Like in this case, you can so exponential function is one kind of basis, and then you can use sine and cosine. You can do the same thing by changing different bases, right? So that's possible. So so that form is kind of a little bit uh, give you some more a little bit more physical intuition what this expansion is about. It's like a projection of vector, right? Another tricky thing, I mean, like magic in this notation is that you can reorder that, and put this like this, right, and put this in here before you write down the dot product of the scalar product. Right? We could do that, and this step is okay. I mean, you can. This is just a number. A number. You put the number in front of, behind it, or in front of it. Doesn't matter, right? But the next step is a little bit string, because you see there's an f cat vector f. There's a cat vector f, and again, now kind of string idea. And these are all directs. Directs, right? Very imaginative. So basically, using this notation, basically truncate the scalar product, and this becomes another kind of vector. This becomes, instead of bracket, the whole thing is like a bracket. So this is a cat vector. This becomes a bracket vector. Just truncate this in the bracket vector and cat vector. So put the bracket vector here and group that together before you multiply by this, the originate. Right? Now you see that the cat vector f is a cat vector f. In order for this two to be the same, and so this is equals to 1. So this is like a. It's a little bit like abuse of notation. Because the original notation, this is used to define a scalar product, but you actually truncate that and define your cat vector, and then do a product between a brag vector and a cat vector and brag vector this way, and get a 1. And the idea is that when you try to divide a lot of this vector manipulation, you divide different equations, you just insert as at will like that. So insert the complete, this is called complete set. This is like our completeness condition. You insert that completeness condition anywhere you like. And then when you see something like the scalar product, you can evaluate the scalar product that way, right? And that's what the idea is, that work. This procedure, a little bit abusive of notation, but it actually works. And this one actually, strictly speaking, this is not a scalar one. This is a matrix. This is an identity matrix. If you have n of these basis vectors, this is n by n square matrix. But we actually have infinite number of that. This is an infinite dimension square matrix, and unit matrix in the n by n infinite dimension. Right? So you can insert any identity matrix and multiply by, these are all vectors. So identity matrix multiplied by vectors still that vector. Okay. That is a little bit the view of what you see, and what you see in later in this semester, maybe you see in quantum mechanics. Okay, so that's that. Okay, so all these Stern Liouville theory, I mean, that's part of the notation for that. Okay, and we'll continue. Any question before we move on?